Okay, hi, yeah, so I'm Kimberlee Dube. I'm a postdoc at the University of Saskatchewan with Suzanne Techmeyer, and I have changed my title a little bit, and I've actually been set up very well for this talk by the previous presentations. So I'm going to look at using N2O as a regression proxy for dynamical variability in stratospheric ozone trends. So, as we, I'm sure, all know, there was global ozone loss in the 20th century caused by emissions of ozone-depleting substances, and then subsequent ozone recovery following the enactment of the Montreal Protocol. So these two panels show the ozone trend from 2004 to 2018 in OSIRIS on the right and ACE on the left as a function of pressure and latitude. And you see they're generally quite similar, and we get this ozone increase of about 2 to 4% per decade above 10 hectopascals in both data sets. But we also see these regions lower down of negative ozone trend, mainly confined to the northern hemisphere and also in the tropics at lower levels. So we want to understand why ozone isn't recovering in these regions. There's lots of theories for this: changes to the BIRA-Dube circulation, an increased tropopause height from the warming troposphere and cooling stratosphere related to greenhouse gases. Maybe there's still some halogen chemistry effects even with the Montreal Protocol, or maybe it's something else. But here I'm going to focus on kind of trying to account for the changes in the BIRA-Dube circulation. So, as we've already seen today, trends in our variable, so here it's ozone, are calculated using either a linear regression model or sometimes a dynamic linear model, but in both cases we need to represent phenomena that affect our variable, so ozone, by proxies. So this equation here is the very typical form of the multiple linear regression, so I call it the standard MLR, and we have proxies for the QBO, ENSO, aerosol, and the solar cycle. And then this, beta linear, so the coefficient on the linear trend is what we're trying to solve for. That's what we call the trend. And this describes the linear change in ozone over time. Typically, we assume that this is related to changes in ozone-depleting substances, but it could also include the effects of any long-term changes that are not accounted for by our proxy variables. And in particular, we do not include long-term changes in the stratospheric circulation here. We are including shorter-term changes like QBO and ENSO, but nothing over, decadal timescales. So I want to know if there is a way to calculate or to control for changes in stratospheric circulation while calculating ozone trends. We want to do this so that we can isolate ozone changes from ozone-depleting substances in order to evaluate the success of the Montreal Protocol. And we also want to understand the cause of these observed negative ozone trends in the lower stratosphere. So the method, which we already saw from Patrick earlier, is to use N2O observations from ACE, and I also consider N2O simulations from WACM, as a proxy for the stratospheric circulation. This idea was originally discussed in this Stolarski paper in 2018, where they used MLS N2O to look at trends in MLS HCl. So here I'm taking the same idea and applying it to ozone. N2O is a long-lived tracer with a tropospheric source that is known, so it provides a quite good representation of transport throughout the stratosphere. So the equation I have here is what I'm calling the N2O MLR, and it is much simpler. We just have our constant, the trend term, and the N2O term. So the N2O proxy accounts for all dynamical variability, so QBO and ENSO are included in this, as well as changes to the BIRA-Dube circulation. I don't have solar cycle and aerosol proxies here. These probably wouldn't be covered by the N2O. I found they were not at all important for the time period I'm looking at, which is quite short, only 2004 to 2018. You probably would want to still include those if you're looking at a longer time frame. So, yeah, I just mentioned I'm referring to trends as this quite short period from 2004 to 2018, just due to limited data. I'm looking at version 4.2, ACE, N2O, and ozone, version 7.2, OSIRIS, ozone, and then I'm also considering a WACM specified dynamics run. So this run has the temperatures and winds nudge to MERA2. And I'm using the Wacom N2O and ozone. So a little bit more about N2O trends. On the right here, you see the N2O trend in ACE. And there's this really strong asymmetry in the lower stratosphere with a negative trend in the northern hemisphere and a positive trend in the southern hemisphere. And this is caused by circulation changes. So what's happening is we're getting increased upwelling in the southern hemisphere relative to the northern hemisphere. So the other figure here shows the age of air trend from era 5. And we see that the air is getting younger in the southern hemisphere and older in the northern hemisphere. So when the air is younger, we actually have more N2O because there's less time for the N2O to get converted to NOx, basically. And we have the opposite happening in the southern hemisphere since the air isn't, or sorry, northern hemisphere, the air is not moving as quickly, so the N2O is getting destroyed. Okay, so I want to use this N2O as a proxy, but before I can do that, I need to remove the surface emissions because we just want the trend only, or the N2O only due to circulation changes. And I'm also going to consider both ACE and Wacom N2O as the proxy, so ACE is maybe a better choice just because it's observations, but there is limited sampling, and of course the instrument will sadly not last forever, so with Wacom we can choose our time period and potentially apply this N2O proxy to any data set. And you see on the right here, I have the same ACE N2O trends, and then also the Wacom N2O trends, and they're very similar. All the regions where they're different are like hatched out, so they're statistically insignificant. So this implies that Wacom is doing a very good job of capturing this same circulation-related variability that we're interested in. So I have my N2O time series with these trends in it, and I subtract the surface N2O trend. So in the middle panel here, it's the N2O as a function of time. The black line is data, the blue line is the fit to the whole time period, and the orange line is the fit just from 2004 to 2018. So during that time, the N2O has a trend of 2.8% per decade. So I remove this trend, I remove it from the data set and then do the regression again to get the last panels, which is the N2O trend only due to circulation changes. And the asymmetry below 10 hectopascals is even more pronounced now. So this final column is what I'm sticking into the regression as the proxy. Of course, the data, not the trends that are shown here. So now we will use this to calculate ozone trends. So the column I have here is just the ozone trends from the standard regression equation. So these are the ones you've seen before. So we already showed OSIRIS, which is on the bottom here, and ACE in the middle, and I've also added in the Wacom trends, and they're all quite similar, especially with this kind of blob of negative trend between about 10 and 30 hectopascals in the northern hemisphere, and this is statistically significant, at least in a couple of the bins. So now we use the N2O proxy, and this is the results. So first look at the middle column. So this is the trend using Wacom N2O. And we see in all cases this region of negative trend above about 30 HPA is gone, or else in ACE it's insignificant now. But we still see negative trend that's actually even more negative than before, lower down and in the tropics. So we can say that maybe the N2O proxy explains the negative trend above 30 hectopascals, but it does not explain the negative trend below 30 hectopascals. And the last column is the same thing, but using ACE N2O. And for ACE and OSIRIS, the results are largely the same as when I used Wacom, but if we use ACE N2O on Wacom ozone, it doesn't work so well. The trend is pretty similar to using the standard MLR. So, of course, using ACE N2O with ACE ozone, we have a perfect sampling match, so there's nothing to worry about. And it seems like it's also okay for OSIRIS, but might not be applicable in all cases, whereas Wacom N2O would be, I think, a pretty good proxy for any data set. So to explain what's happening a little bit more, we can kind of compare the trends to the N2O trend and the relationships between N2O and ozone. So in these panels on the left, I have the correlation between OSIRIS, ozone, and ACE N2O. So where it's blue, they're anti-correlated, red, they're correlated. And this correlation is kind of equivalent to the sign of our N2O regression coefficient. So where we have anti-correlation, that coefficient would be negative, and correlated is positive. So below about 30 HPA, ozone and N2O are both controlled by transport. So N2O is a tropospheric source and is long-lived, whereas ozone is a stratospheric source and long-lived. So that's why we have this anti-correlation. And we also know that in this region, the trends from the standard MLR have the same sign. So I put the ACE trend here, and it's negative in this northern hemisphere below 30 HPA. And the contours on these other plots show the ozone trend. So if we look at the middle panel, black is where the ozone trend is negative, magenta is where it's positive. So we're still focusing on this same region. So here I'm looking below 30 HPA, so this black region mostly in the tropics. So here, since the N2O trend is negative and the ozone trend is also negative, but our N2O coefficient is opposite in sign, we end up actually lowering the ozone trend by fitting N2O in this region. So yeah, the ozone trend becomes more negative. So the effect of long-term circulation changes is actually having the opposite effect of maybe what we want. So it cannot explain the ozone decrease in this region. But between 10 and 30 hectopascals, so now we're looking in a bit higher, ozone and N2O are correlated. In this region, the ozone lifetime is controlled by chemical production and loss. So here now we're focusing on this black blob in the northern hemisphere. So there, the N2O trend is still negative in this region, but now the ozone trend is, I guess it's also negative. So our trends have the same sign, but now we have the positive correlation. So fitting the N2O actually lowers the ozone trend in the northern hemisphere, and conversely it increases the ozone trend in the southern hemisphere. But so our ozone trend here is becoming less negative. So on the other panel here, this is the trend from the N2O MLR, so we don't have this black contour region anymore. There's a little bit of zero trend here. So in this region, we can say that long-term circulation changes that are accounted for by N2O anyway do explain the ozone decrease. So in conclusion, observations show decreasing ozone from 2004 to 2018 in the tropics and northern hemisphere. We can use N2O as a proxy for stratospheric circulation when calculating these trends. And by doing this, we see that negative ozone trends above 30 HPA can be explained by changes in stratospheric circulation, but the negative ozone trends below 30 HPA cannot be explained by this method. So potentially there's something else. In the tropics, the increases to the tropopause height could be important. I'm not accounting for those right now. And there could also be some halogen chemistry that we're not considering. I didn't show it, but we also see this similar to N2O. There's a very clear asymmetry in HCl, so there's actually an HCl increase from transport in the northern hemisphere. So perhaps this higher HCl is actually more directly contributing to the ozone loss. And that's all. Thank you.